Hey everyone, it's February 28th, 2022. We're going to continue our lesson in statistics. This is College of the Sequoias. We are studying the binomial probability distribution. This is 6.2 in our book. We did go over some of the content last time. Let me give you a little refresher because we need to check these each time. So to see if something is binomial, we need it to have a fixed number of trials. And the trials, they need to be independent. Trials must be independent. I used to do these in a different order, but I think talking about the two where they're trial-based is worth putting together. Then we need two mutually exclusive outcomes. And finally, the probability must remain fixed between trials. Probability can't change between trials. Which is kind of like, these two are kind of related. Like when we saw when you draw a card from a deck and you don't put it back in, it changes the probability for the next draw. And so those are not independent trials. So we won't look at anything like that. And we went over some examples of these, like identifying. You just got to walk through all of the things and make sure they all apply. And then we got down to the formula. The probability of X is, ooh, loud chime. It's N choose X. And then we have P raised to the X power. And then we have 1 minus P raised to the N minus X power. And this is hell. This is a horrible, horrible process by hand. So in terms of StatCrunch, we're going to go stats, calculators, binomial. And what we need for that, the things we need to use that calculator, we'll load it up in a second. We need to know N, we need to know X, and we need to know P is the probability of success. So N is the number of trials, X is the number of successes, and P is the probability of success. Before I do that, we need to make sure everyone's on board with some, like the inequalities and the words that go with them. Because maybe I can show you why. Let's bring it up. Let me load my math lab, get some StatCrunch going on. Maybe motivate this topic, why I'm going to pester you with this shit. Click on it. Come on, load up. Every time I click that, it does nothing. Let's try refreshing. Well, that's fun. Go back Try it this way without going into our direct course, but the main course. Is my mouse not working? Let's try using the click pad. It says it's loading. Just not being patient. That's the problem. Really? Well, while that's loading, I am going to start going over the topics. So when we see, so the symbol, the less than symbol, you'll see words that say less than, they'll show up in the sentence. You might see fewer than, at most, or no more than. They're all implying less than or less than or equal to. These two tend to be the less than or equal to ones. And those ones right there tend to be the just strictly less than. Then there's the greater than. You'll see more than, greater than. And then we've got like greater than or equal to. Here's you'll see at least shows up. Or no less than. The ones that StatCrunch likes to use are these two for that. They generally don't do the no more than, no less than. That sounds like some Price is Right bullshit. Leave that on the screen for a second. Hopefully that loaded. It did. Awesome. Just open StatCrunch. And so we've got stats, calculators, binomials right near the top. So far, we've used custom and we've used binomial right now. The next one will be the Poisson distribution. We'll be doing that today, and I hope we get on to the normal distribution today. Look at binomial. And it asks for NP. There's my N, there's my P, there's my X. And this is why I brought up the symbols. It's a drop-down menu. And so like when they give you the word problems all the time, but they don't have symbols in word problems. So we need to be able to identify what they're actually asking so we can translate it to this. Okay. We'll do that. Let's put some examples up and we'll come back to this and use that to do it. So example number 1. Oh, let's change this number. I'm guessing maybe it's probably gone down as inflation has gone up. People haven't had as much money. Let's say 28% of car owners have 3 or more cars. We will sample 20 homes. to see if they have 3 or more, to see if the family owns 3 or more cars. I don't fall in that group. My wife and I have 2, 1 each. And mine's a little moody right now because it's an electric vehicle and I didn't start it for a year. And now it doesn't want to turn over at all. I gotta get it charged. But I can't get to the charger because it's in the trunk and everything's locked electronically. So I gotta almost break into my car to do this. Let's see. So question A. In fact, let's list all the questions. How many are, if we surveyed 20 homes, what's the probability that, in fact, this is the sentence that's going to go with all of them. What is the probability that and then I'll put A down here. A, we find exactly 5 homes of the 20. Then we'll look at B, that less than 4 then. Less than 4 homes. 4 then, that doesn't make sense. Less than 4 homes. And let's see, let's do at least 1 home. Let's see if I can split this up and be clever. Can I go split screen? I almost want this one on the left. That's annoying. And then I'll put up my other writing over here on the right. So let's look at exactly 5 homes. What we have in this problem, we can go through the information. It says 28% of car owners have 3 or more cars. We're going to call that our probability of success. So P in our stuff is going to be 28%. And since we're doing this in mathematics on it, we have to shift to a decimal by moving it left twice. So that comes from there. It says we will sample 20 homes. That's the total number of places checked. N equals 20. And then X is in each problem. And let's just think about the things that we have to check. Do we have a fixed number of trials? Let's make sure this is binomial. Do we have a fixed number of trials? Yes, we've got 20. Are they independent trials? Assuming we don't just go down the street and hit 20 homes on the same street, we just sample 20 homes throughout a town, like from all over the place. There's no reason to think that they aren't independent. If they are on the same street, you might be hitting a rich part of town or a low income part of town. And so that would definitely impact it. So we're going to assume they sampled from all over the place. Is the probability changing? Nope, it stays at 28%. Every house should be 20% chance that they have it. And are there 2 mutually exclusive outcomes? Yes, they either have 3 or more cars or they don't have 3 or more cars. So we meet all the criteria. So let's apply this to what we're using in StatCrunch. I'm going to put the N equals 20 over here and P equals 0.28 right here. And now it says exactly 5 homes. Exactly is an equal sign. And it came with 5 already automatically in. That just happens to be the way it's set up. It tells us our probability right here. So it says the probability is probability that x equals 5 is 0.193, and I'll round to 4 decimal places, 3. 1933. Notice that it's got a red here. It shows us what section of the graph we're talking about. It actually will show us if this is a set of skewed data or not too. Well, I guess this isn't the data. This is a probability calculator in mind. That's all dependent on the probability, as we'll see later on. So that was exactly 5 homes. The next question was that less than 4 homes. Less than 4 homes would be less than 4. It doesn't say less than or equal to, so we're going to go with less than 4. And it's got 0, 1, 2, and 3 lit up. That looks good. 0.1466. And I'm just going to point out real quickly, this is probability that x equals 0 plus probability that x equals 1 plus probability that x equals 2 plus probability that x equals 3. And if we want to do that in the formula up top, we would have to do it for each one of those. You'd have to do all 4 of them, which would be a pain in the ass. Good way to possibly screw it up. So StatCrunch is definitely helpful here. And then we look at least 1 home. What does that mean? At least 1, let's go look at what we talked about. At least 1 was the greater than or equal to. So here we're looking at the probability that x is greater than or equal to 1. We have a couple ways we can do this. Directly. We can put it in directly and just choose those values and click compute. And now the only one that isn't red is this little tiny black dot over here. So 1, 2, 3, 4, all of them are red after that. And it gives us a nice big percentage. 86 to 4 decimal places. This is also another good example of what we were talking about when you could do either or, because sometimes they'll ask you linked questions. They might start off with what's the probability that 0 homes have it. So I'll just add that in as a bonus. Exactly 0 homes. Now remember the way probability works. We could add, if we add 2 different probabilities and they cover all the probabilities, like probability that x is equal to 0 and probability that x is greater than 1. This covers all the possible numbers here. 0 is the lowest number for x. You can't have like a negative number of cars. I guess theoretically you can if you owe money on a car, but that doesn't really make sense, really. Or you could have 1 or more cars. Remember, they add up to 1. So I could find probability that x equals 0 simply by subtracting that over. And we get probability that x equals 0 equals 1 minus the probability that x is greater than or equal to 1, which is 1 minus 0.9986. And I think that's 0.0014. And we can check that. I could just go with less than 1. Less than 1 shows it. I could say less than 1, or I could say equals 0. And they both give us that 0.0014 that we just got right over here. They could also ask something like this. What's the probability that the number of homes is between 6 and 12? Well, between 6 and 12 doesn't actually say include 6 and 12. So this would be 7, 8, 9, 10, or 11. As opposed to what they say when they want to include those, they'll say like between, let me just erase that. So I write it and it looks intelligent. Between 4 and 9. And then when they want to include the n values, they will say inclusive. Inclusive or including those values. Well, we could check it. Remember, this is the same as doing probability that x equals 7 plus 8 plus 9 plus 10 plus 11. Doing all these probabilities going down the list. Here we can do it, and up here in the binomial calculator, there's a between click. So if you click on between, it changes the arrangement. Now the symbols for the between are stuck. You don't get to change the symbols. So for between, we can't change the symbols. So we just need to make sure we're using what works. I have to use the less than or equal to, and what I'm starting with is between 6 and 12. I can't actually put 6 and 12 in here. I have to put probability that x, or 7, which was my lowest number, 7 is less than or equal to x, which is less than or equal to 11. And I can put those in. Now that I got them in, I click compute, and it gives me the probability. 3142. And if we want to do 4 and 9 inclusive, that's actually including the 4 and the 9, not just the 5, 6, 7, 8. So here we can actually put the 4 and 9 directly. And this gives us 0.82297, rounds up to 30. Sneaky. This is one of those rare exceptions where rounding to the last place means you got to round to the second to last place. Unfortunately, this is our big unfortunately for StatCrunch. Unfortunately, StatCrunch doesn't calculate the mean and standard deviation for us. But they aren't too bad. The mean of this distribution is n times p. And the standard deviation You're going to do n times p, and then you're going to do 1 minus p, and then you're going to take the square root of all that. So in our problem, we had n was 20, and the probability was 0.28. So we get our trusty calculator. And I get 5.6. So that's my mean. And notice n times p is right here. So I can actually just put that directly in. I've already got n times p, which is mu of x. I've got 5.6. And now I need 1 minus p, or 1 minus 0.28. And I made my square root sign too long, so I'm going to change that. So let's see, this is 1 minus 0.28 is 0.72. So I've got 5.6 times 0.72. And that is 4.032. And I take the square root of that, and I get 2.00798, or 2.0080 to 4 decimal places. So let me get rid of that right there because it's making it look funny. That's a P. These, they will ask you information on. You do need to know these. If you have them on a flashcard or something, readily usable. They come up a lot. They will ask you mean and standard deviation. So make sure you know how to use them. And you're really just plugging in N and P and then just doing some calculations. I'm going to show you something on the calculator. Let's switch this probability to 0.5. I can go 10. I'll put 10 in the middle, just so that we're looking at the middle. Notice that when probability equals 0.5, like I have here, this gives us a bell-shaped graph. It's nice and even on both sides. Now, when P is really low, let's just throw in a low value and see what happens. Let's see if we can reason through what happens before I do it. If P is low, it means there's a bigger chance that I'm gonna, I'm not likely to hit it. I don't know, let's see. I don't know if it's easy to reason through. It's kind of easier to reason through when we see it. So when the probability is low, the chance that we're going to hit a low number of homes is higher than hitting a large number of homes because the probability is low. And so our hump is over to the left. This leads to a skewed right graph, skewed right data or a graph. And when the probability is high, the opposite is true. If we have like a 90% chance of picking a house with a home, we should be getting some, up in the, I don't know, 15, 16, 17 ohms, something like that. Let's take a look what happened when we put 0.90. The hump is over here on the right, and the data to the left narrows down. And look at the numbers. I think the numbers really help show it. 12 is our lowest here. So like 10 doesn't even show up on the chart. When I had 0.5, 10 was in the smack dab middle, and we could go to the left and to the right. So it shifts. Not only does it shift the values in the graph, but it skews it. In this case, it was skewed left when we had it high. And we desire bell-shaped data, or bell-shaped. And so if P is high or low, what can we do about it? Can we trigger a bell shape by changing anything? And it looks like the only thing we can change is the number of houses we ask by changing the number of trials or experiments. So let's see, let's put this back up to, let's go 0.85. And this is 10, let's make it 30. Starting to look a little bit more bell-shaped, isn't it? The tail on the left is still a little bit longer, but it's getting closer. Like if we did like 10, it's really skewed. The hump is all the way to the right. So we saw 30. Let's see if we go 40. It's getting even more bell-shaped. What if we went something like 100? Now it's looking pretty bell-shaped. Yeah, it's probably still a bit longer to the left than to the right, but it's getting harder to tell. What if I went like 1,000? Now it's got that bell-shaped distribution. So what we want to do is raise the number of trials. But how many? Do I really need 1,000 to get it? Because 100 looked pretty darn good too. Does 50? 50 looks pretty good too. So how do they determine that? What we want to do to force a bell shape, or force approximately bell-shaped, we want to pick n such that n times p times 1 minus p is greater than or equal to 10. Okay. So let's see what happens. How can we, let's give some examples and see what we can do to trigger that. Let's go with if p equals 0.21. What should n be? So n is the value I don't know. I'm going to plug that value in now. I've got n times 0.21 times 1 minus 0.21. I want that to be greater than or equal to 10. Let's see, if we multiply this out, well, 1 minus 0.21 is 0.79. 0.21 times 0.79. No, I just made it worse. .21 times 0.79 is 0.1659. So I've got 0.1659, n is greater than or equal to 10. If I divide both sides by it, oops, I did that completely the wrong way. I want to divide 10 by the other side because we're getting n by itself using some algebra techniques. And what do I get? I get n equals 60.27 or 60.28 if I round it correctly. N has to be a whole number. I can't check 60.28 houses. So in a circumstance like this, you always want to round up. We want to pick n to be greater than or equal to 61 homes. If the probability, or 61 in general, not homes, but in the last problem we were talking about homes, but in general, we would want 61. What happens if it's exactly 0.5? Like, let's make n pretty low and see what happens. I guess it's kind of bell-shaped, but we want more than that. It's not enough. So let's just walk through it. We know that n times p, I'll rewrite it again because it's off the screen, needs to be greater than or equal to 10. We've got n times 0.5 times 1 minus 0.5. And this is n times 0.5 and then another 0.5. This is 0.25 when you multiply 0.5 together. So I get n is greater than or equal to 10 over 0.25. N is greater than or equal to 40. In general, you want at least 40. P equals 0.5 is the most favorable condition. Has the lowest n. Anything above that's going to have a little bit higher. But we like bell-shaped. Okay, so that's the binomial distribution. Any questions? I like having StatCrunch up on one side, kind of small, and the screen up on the right, bigger. I hope you guys like it too. All right. So let's take a look at 6.3. And this is the word for it. And it's not poison. It looks like poison. It's Poisson. Poisson. That's how it's pronounced. It's some French guy. Good to know. Almost every single problem that uses a Poisson distribution says it. So what are our requirements for a Poisson distribution? Like the binomial had 4 different things. What does the Poisson distribution require? We're looking at intervals or regions. Intervals is often associated with time. So like a minute long, 30 seconds, 6 seconds. 6 seconds is a round in Dungeons and Dragons. That's an interval of time. Or it could be a year if we're talking about something that doesn't happen very often. So what we want, and it also could be area. Like if you're looking at, you've got a very, very low pressure gas inside a giant tank. An area could be like a cubic centimeter inside that tank, and we're looking at the probability that we'll find a piece of gas, a molecule of gas in that cubic centimeter. That kind of idea. So an interval or region, we want the probability of 2 or more successes is 0 if we make the interval small enough. So for like getting a phone call on your phone, maybe we would drop it down to like 3 seconds. You can't feasibly answer the phone, hang up. Well, I guess you could, but actually hear who's on the other end of the phone and decide if you want to hang out, like, stupid survey call or your car warranty has been extended call. Maybe 3 seconds or 2 seconds. Eventually, you can't get 2 phone calls in that time period. So we can change the time limit to find it. B, the probability of success is the same for 2 different intervals of equal length. And like the phone call thing I was just talking about, let's say you go from 4 o'clock exactly to 4 o'clock 3 seconds later. That's a 3-second interval. And then we wanted to look at like 4:31 and 30 seconds to 33 seconds. That would be a 3-second interval. The probability should be the same between any of those 2 intervals. And the number of successes in any one interval. Is independent of the other intervals. And here we're obviously assuming no overlap. We don't want to do like 4 o'clock to 4 o'clock and 3 seconds as one interval, and then 4 o'clock and 1 second to 4 o'clock and 4 seconds, because there's some overlap. So the probabilities will affect each other. You're going to love this first example we're going to do. How many of you love chocolate? You guys like chocolate? Oh yeah, everyone said yes. All right, so the food defect level, action levels. Let's see, is it all on here? Yes, So list all the things that make it defective. Let's go for chocolate. Chocolate, insect filth. Average is 60 or more insect fragments per 100 grams. That's their average when doing when they sample 600 gram samples or more. Like if you were going through a Hershey's factory and doing it. So what does that mean for us when we are eating chocolate? So the FDA, Food and Drug Administration, has set the food defect action level of chocolate to 60 insect fragments per 100 grams. And so if I wanted to see what is the rate per gram here, I've got 60 fragments over 100 grams. This is 0.6 fragments per 1 gram. Okay. Does that mean anything to us? Well, let's put it in perspective. A Hershey bar is 1.55 ounces, or OZ is the abbreviation for ounces, which is approximately 43 grams. And so we are going to look at the probability. What is the probability that in a Hershey bar, we have exactly 3 fragments? Fewer than 3. And then let's look at like at least 10. Now you're, oh, oops, sorry. You may be going, it's not that high. Well, let's take a look at it. I'm going to show you the formula and you'll never use this. So the formula for the Poisson distribution is the probability of X equals lambda T to the X power over X factorial times the exponential function E to the negative lambda T power. Now, lambda here is the rate. That's pronounced lambda. In fact, it's even spelled lambda. It's a Greek letter, lambda. It's the rate or average number of successes. And T is the interval. Often it's time, and that's why we use T. And again, X is obviously the number of successes. So in this problem, I am calling a success the chocolate having 1 fragment. Do not do this by hand. Oop. Not by hand. In StatCrunch, we're going to have stats, calculators, Poisson. I just showed you that formula so you would know what it looks like. I never expect you to use it. I don't expect you to use the binomial one, but that one's at least doable in a calculator. You know what everything is in a calculator. It's just, you can do this in the calculator too, but you may not be comfortable with exponentials and anything like that. So we're going to do stats, calculators, Poisson. And what do we need for stats, calculators, Poisson? Let's take a look at it and see what it asks when it pops up. It wants the mean. So you need the mean. U of X. And you need X. And so mu of X, thankfully, mu of X is easy. Mu of X is lambda times T. And sigma X, square, or the standard deviation, is also easy. It's the square root of lambda T or the square root of the mean. So what does that mean for our chocolate problem? We need the mean. The mean is lambda. The rate that we calculated was 0.6 fragments per 1. And in this case, T was not time. It's an amount of a product. And we were looking at the interval is 43 grams, 1 chocolate bar. So mu of X 0.6 times 43 is 25.8. So let's look at our examples. We had exactly 3 insect parts. And by insect parts, they mean like larvae, eggs, wings, a leg, you know, the animal gets crushed in the process of making the chocolate, and it just like kind of like one ant can get spread across several pieces of chocolate, be mixing it. Let's check it over here. Mean is 25.8. And we have the same drop-down choices we had before. And we want exactly 3. So choose 3. The probability that X equals exactly 3 is really low. Oh, that's good. I got 0.00 shitload. That's a shitload of zeros. 7 zeros and then a 2. So effectively, not really a chance of 3. What about fewer than 3? Fewer than 3 would be X is less than 3. That's even worse. It says 2.2441 E minus 9. This means 2.2441 times 10 to the negative 9. And when dealing with the 10 and exponents, it tells you how to move the the decimal point. This is I'm going to put the 2.2441. The negative 9 is saying move this value left 9 places. left 9 places for the decimal point. It's negative. So I go 1, 2, 3, 4, 5, 6, 7, 8, 9. And all of these have zeros since there was nothing there. So it's even lower than x equals 3. All right, well, what about at least 10? That was B. C, at least 10. The probability that x is greater than or equal to 10 . 0.999, and if I wanted to round to 4 decimal places, another fucking 9. So every insect bar, or every Hershey bar has at least 10 insect fragments. What about 20 or 30? Like, when does this probability get low? Well, we can check it. 20 is at 0.89656, which is 66, which is 89.66%. So at least 20 fragments is still likely. Thirty fragments. $0.2284. So now it's gotten low, but that's greater than 30. So kind of puts a new spin on chocolate, doesn't it? You're welcome for that. Let's look at one from the homework. Oops. So let's see. I want that one. Where is my internet? I don't want that one. I want the other one. It is that one. It's over here. Nope, it's right there. Assignments. You know, what's even better is when I do this class in person, I bring in a bag of M&Ms and I give everybody a bag of M&Ms and we count all the colors because we use it later on in the class. But then after everyone has eaten those M&Ms, then we do this chocolate problem because that's just kind of the asshole that I am. I think it's great. No one has left their room yet wanting to throw up, but I think I'll get someone eventually. I think it's number 19. Let's take a look at it. Let's see if I can bring this up. Will it condense the window if I do? Yes, it does. So this is number 19 from our homework. And your numbers will vary, but I think it's worth going over how to do it. It says for the past 104 years, a certain state has suffered 24 direct hits from major hurricanes. And that is composed of categories 3 to 5. on the hurricane scale. Assume that this was typical. And the number of hits follows a Poisson distribution. Complete parts A through D. A, what is the probability that a state will not be hit? The state, not a state, the state in question will not be hit by any major hurricanes in a single year. So to do this in StatCrunch, we need two things. I need the mean and I need X. We need mu of X and we need X. Mu of X was lambda times T. So we need T really effectively. So we need lambda and T, right? T is a single year. That's they're giving us a time range. It's 1 year. Did they give us lambda? They've thrown a couple numbers at us. They said the last 104 years, the state suffered 24 direct hits. Well, they didn't say if there was like 3 in 1 year and then nothing for 10 years, you know, anything like that. So we can't go off that. We can just do like an average. And that's what lambda is looking for. Remember, lambda is an average or a rate. So lambda is going to be the 24 direct hits divided by the 104 years. Let's see, that ends up being 12 over 52, which is 6 over 26, which is 3 over 13. Damn, does reduce all the way, which is approximately 0.230766923. I'm going to use all those because I don't know how much it's going to affect the answer. So use all of them. So I need lambda, or I need the mean. Mean is lambda times T, and which is just that times 1. So it's just that same value. 0.230766923. And now I need to know what X is. The state will not be hit by any major hurricanes. What should I say X equals here? Pop up chat, see if anybody chimes in. How many hurricanes are we looking for? None. 0. Correct. Thank you, Gabe. Not any means none, which means 0. So let's put this in our StatCrunch. Let's get my StatCrunch window back up. Whoa, what did you do? And I'm going to change my mean. My mean is 0.23, and I'm going to put all of them in because I don't know what's going to affect the answer. And I'm going to be mad if I miss the rounding by 0.0001 and I didn't know it. And I just thought I got the answer wrong because I was off by rounding. So don't be lazy. Put the entire number in when you're doing it. And as Gabe said, this was probability that x equals 0. Oh, look at that curve. That's skewed right big time. It goes down to the left. So probability that x equals 0, according to StatCrunch. Blessed be the StatCrunch because it does all the math work for me. Well, most of it. I had to do mean by hand. I had to use a calculator. 0.7939226. I don't know. I don't remember how many it asked for, so I wrote them all down so I can go look. To 4 decimal places, 0.7939. Excellent. What is the probability that a state will be hit by at least one? At least one is 1 or more, or x is greater than or equal to 1. So that's what we're looking for here. Probability that x is greater than or equal to 1. It should be, recall, we said probability that x equals 0 plus probability that x is greater than or equal to 1. Doesn't matter what the thing is, should equal 1. So without even going over to StatCrunch, I can calculate this. One minus 0.79392266. 0.20607734, which to 4 decimal places is 2061. I'm going to type that in, but we'll go confirm it before I hit enter. You know, every once in a while, the teacher's wrong. I do make mistakes. Not many, but they happen. It's greater than or equal to 1. That's the number I got, 20607734. So I like that number. I'm going to go hit enter. I'm good with that. That's my final answer. Is this unusual? It's a sub question. So what makes something unusual is if the probability, whatever it may be, is less than 0.05. This is not. 20.2061 is greater than 0.05. So this is not unusual. Probability the state will be hit by at least 3. The state's getting fucked up if it gets hit by 3. Am I right? That's a lot. As happened several years ago. So whatever state they're talking about, this happened to. I'm guessing Florida. Florida is the most hurricane-prone state because it's right off the Atlantic Ocean and the Gulf. Let's go calculate this. The mean hasn't changed. It's still 24 over 104 years. So I just got to change these values. Probability that x is greater than or equal to 3 is 0.001724447. Notice this has a between also. We haven't used it, but it's got a between. Let's go put that in. I forget what the last question is. I wanted to go through the whole problem. because a lot of people get to this and go, what the hell? Is that a 6? 001. Okay. My handwriting is sloppy. And it's wrong the way I wrote it. Look at that. It is 0017. Okay. 0017. There we go. And then this is the one of the times we don't round up. Is this unusual? Yes. This is less than 0.05. So it is unusual. At least 2 major curve. Okay, so D is asking us the same thing, but for the next value. So let's just do it real quick. Make sure there's nothing sneaky in this problem. As happened last year. I don't know when this was recorded or this book was written, but we're getting 0.022864442 or 0.0229. And this is also less than 0.05. So that's unusual. And that's it for that question. And that'll wrap up chapter 6. Let's take a look at, is there any questions on Poisson distribution? Let's see, chat pop up. No. I'll mention one more thing because I know they tend to have problems like this. They'll tell you like between 8 a.m. and 9 a.m. So and so experiences an average of 4.2 visitors, callers, whatever it is, per minute. And then they'll ask you something like, what is the probability of something going on between 8:10 and 8:20? So here you can't just go with the 4.2 because you need lambda x, you need mu, and mu requires lambda t. Lambda is that rate, it's that 4.2. T, it's in per minute. There are 10 minutes between 8:10 and 8:20. So you got to multiply by 10 there. And mu of x would equal 42. So you'll see problems like that. That's what's going on in those. And they'll also tell you it's a Poisson distribution. I think they got a problem about like a drive-through at a fast food place. Calls per minute or some shit like that. All right. Let's take a look at chapter 7, the normal distribution. The normal probability distributions. And this is our world of continuous data. Chapter 6 was our discrete variables. These are continuous, well, I don't want to say data. Let's say continuous random variables. That matches the wording on chapter 6. So here we're looking at things that are measured. Time is a great one on that list, but length is also. Time, length, area, volume. Anything related to those? Oh, weight. And let's just go straight out the gate. Where are we going to be looking? Stats, calculator, normal. So I'll get this loaded up over here on the screen. It's down here under N, stats, calculator, normal. Notice it requires mean. Mean. It requires a standard deviation. And it requires, oops, not an equal sign. And it requires X, the value we're looking at. I want you to note that our drop-down menu only has two symbols, less than or equal to or greater than or equal to. For continuous data, or for continuous distributions, the probability, oh, I don't need the parentheses right away. The probability that X equals a specific value is 0. So that means less or greater than or equal to is the same thing as greater than, because they're the same values. They can result in the same thing. And then less than or equal to is interchangeable on continuous data with just less than. So however the problem's worded, that's how we're going to use it. Why might you say? Well, picture it as this. And this comes with related to the first or the rules of normal distributions. The area beneath the curve equals 1. And is thus the probability. If I go for something that is a specific value, if I do a specific value, I am making a rectangle. Oops. Like I can always treat this as a rectangle under the curve. Finding that area if I do a region. If I do a region between a curve. Continue. If I do a region between the curve, I'm always going between two values. I can find that area. If I do a specific value, it's like a rectangle that's 0 wide. or width, not length, but width. And we know the area of a rectangle is length times width. And in this case, since the width is 0, it's going to be 0. And so you can't have that problem. But it's important to note that area beneath the curve equals 1. It is symmetric. Notice that it's perfectly bell-shaped. It's perfectly bell-shaped. And symmetric around the mean. Which means the left half mirrors the right half. In shape. And I said it's symmetric about the mean, but since it's perfectly bell-shaped, the mean is the same thing as the median or the mode. That does not look like the word median. I'm going to fix that. That doesn't look any better. Fuck it. If we look along the bottom of the bar, it's the left side is negative and it goes up as we go to the right. So the axis underneath it, axis or number line underneath it, increases from left to right. And it kind of shows it here, but notice that red never actually touches that axis, that line, that number line. The graph never touches the number line. Which means the probability for any region is always greater than 0. It can never equal 0. It can be infinitely small, almost undetectable by the human eye, maybe even indetectable by the human eye. But there is always a very, 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 very small probability. Something to know about the bell curves. If I have a bell curve like this, let's pretend that's a good bell curve. Let's say sigma equals 1 here. And I have a second bell curve where sigma equals 2. Sigma equals 2. The sigma equals 2 is going to be shorter in the center, but as it goes outwards, it's higher. That's true for all of these. The larger sigma is, the smaller the hill is, but the wider the outside parts are. And it's like it's a trade-off. The area's got to stay 1. So if the hill goes down somewhere, it's like pushing a mound of sand. We have a certain amount of sand that the hill goes down, the sand's got to go out. God, that's a really good example of sand. I like that. Sand is a good thing. And this, as I said, this keeps the area at 1. So we can tell two things. We can read this two ways. For a given area under the bell curve, let's call it a region. Between two values, under the curve. Let's say we're going from this value to this value. So we're talking about that region right there. X1 and X2. For a given region under the bell curve, we can say that it represents and what I'm showing right here is the probability that X is between X1 and X2, like our between button has over here. It can mean two things. A, it's the proportion of the population that can have that trait. Or characteristic or job or whatever we're looking at. If it's not a person, if it's a car, we could be talking about the engine size. Well, engine size is not continuous. The amount of miles driven on a specific car. It's the proportion of the population with that trait. Or B, a randomly selected individual from that population. How do I want to word that? For a randomly selected person. Let's change that. Sentence reads a little bit better. For a randomly selected person from that population, it represents the probability that they possess that trait. The homework will often tell you that it's normally distributed. Homework will frequently say that it is normally distributed. Like the Poisson one tells you it's Poisson. This one will tell you that it's normal. A very common one that I don't think has ever changed, I still think is the same, they've never changed it. The IQ test. That's the one that's at that Stanford Binet. I think it's test.com. I assume it's all of mankind, all of humanity. The mean is 100 with a standard deviation of 15. So if I put that in here, you can see what the distribution looks like. Something nice that this thing, the StatCrunch shows you, see this 68, 95, 99.7 ticks? It's a button in StatCrunch. This is the empirical rule values. Watch what happens when I click it. Look at the number line. It goes 60, 80, 100, 120, 140. If I click it, it adjusts to match those values. This is the empirical rule. Okay. So let's say, let's just look at an example. What's the proportion between 85 and 130? We want to do between 85 and 130. (0.8185941) or 81.8%. So if we did check to everyone, the amount of people that are in that range is 81%, 82%. Or if I picked a random person anywhere on this planet, picked them randomly, if there's an 81.8% chance that they have a score between 85 and 130. So let me write those down, the two options. Because I said there's two ways to interpret that value. 81.8% of the population has a score. Between 85 and 130. And B, the probability that a randomly selected person has a score between 85 and 130 is 81.8%. I do not like the way that between looks. Let's look at what's the top 10%. What IQ scores represent the top 10% of humanity? Well, here I'm asking for what these values are. And since I want the top one, I only want I don't want a range between, I want one of the end sides. So I'm going to come back over to standard. And let me just put 100 to see which way everything's going. X less than 100 is to the left. I want to the right. I want greater than. And exactly 100 is 50%. I don't know what this value is. I don't need to guess values to find it. I mean, I could try guessing values and see what I get and try to keep going until I get to 10%. Or instead, you can come over here and change this value. So in StatCrunch, I am doing this. Probability that X is greater than or equal to blank equals 0.10. I'm putting the 10% in on the right. And I click compute, and it will give me the score. Probability that X is greater than or equal to 119.22327. I don't know that they use decimals on the IQ. So which way do I want to go? Do I want to go up to down to 119 or up to 120? IQ is a whole number. So the way you figure it out, it's kind of like we're drawing the little bit of the number line. I've got 119.2237 right here. I'll just do 119.22. If I go down to 119, it's to the left. And if I go to the right, it's 120. I'm exaggerating the distance to make it visible. And right now, we are currently shading this. So what's going to happen if I go to 120? If I use 120, my region is only this. I won't have the top 10%. And I can show you that. We can do 120 right here and check it. 120 is 0.091, the top 9.1%. So, and if I use 119, it's going to include this part over here on the left too. So it will be above, or it'll be more than the top 10%. Let's just take a look at that. 10.26. We always want to choose the method nope, getting rid of the color. Choose the method that captures the full amount of what we're looking for. Here it's the 10%. 120 does not get all 10%. So we're going to go with X equals 119. X is greater than 119 or scores above 119, scores 119 and higher. And I think we'll call that a wrap for today. You guys got any questions? We'll do more on this section on Wednesday, and we'll do 7.2 and hopefully chapter 4 on Wednesday. We'll get all that done. Chapter 4 will not be on the test. That's taking place next week. The midterm is next week, starting on Wednesday. So we're going to do 7.2 or finish this and do 7.2 on Wednesday. We're also going to look at chapter 4 for next week, or for the afterwards, just so that we don't fall behind on the lecture and stuff. But you won't have the homework for chapter 4 won't be due till after the midterm by quite a bit. And you're not tested on chapter 4. And so you'll have plenty of time to get all the homework done for these sections. The midterm starts Wednesday, and you'll have through Sunday, I believe, to do it. I think I set up through Sunday. Any questions? Well, then I hope you guys have a wonderful day. Keep up the good work. Remember, if you have questions, email me or hit the Ask the Instructor in the homework assignments. Thank you.